Right. So now we will discuss some problems on metric spaces. Before going to discuss the tutorial sheet, I need to recall what is the metric space. So X is a non-empty set and D is a function from X cross X to R, the set of real numbers. And D is said to be a metric if there are four axioms, that is MS1, that is the distance of X comma Y is always non-negative. And the second axiom is the coincidence, that is g of X comma Y is equals to 0 if and only if X is equals to Y. And MS3 is equals to symmetric property, that is the distance between X comma Y is equals to distance between Y comma X. And the fourth axiom is triangular inequality. D of X comma Y is less than or equals to D of X comma Z plus D of Z comma Y. So now, based on this definition, we have discussed a variety of examples in class, but we will discuss some problems which are mentioned in the tutorial sheet, right? So now, number one, so A is, D is a function from R cross R to R, right? And A, that is the distance of X comma Y is equals to modulus of X square minus Y square, all X comma Y belongs to R, right? So now I am going to determine whether this D is a metric or not. So generally, there are two axioms we can emphasize whether they are, if it is not a metric, right? Of course, the first axiom, obvious because of the modulus is a non-negative. And the second one, we need to verify whether this one is a satisfying the coincidence or not. Let us take MS2 verification. Let X is equals to 1 and Y is equals to minus 1. So clearly X is not equals to Y. What about the distance of X comma Y is equals to modulus of X square, that is a 1, X square minus Y square, that is equals to 1 minus of minus 1 whole square, that is equals to 1 minus 1, that is equals to 0. So what happened here? The distance of X comma Y is equals to 0 does not imply X is equals to Y. So clearly the second axiom, MS2, fail, right? So that's why this D is not a metric. Once if it is not a metric, and hence it is not a metric space under this metric. What is the second one? Second one is the distance of X comma Y is equals to square root of modulus of x minus y. What about this one? We will verify one by one condition, right? Let us take x comma y belongs to the real. And clearly MS1, right, modulus of x minus y is greater than or equals to 0. That implies the square root of modulus of x minus y is greater than or equals to 0, implies the d of x comma y is greater than or equals to 0. So clearly d is non-negative. What is the MS2? That is the distance of x comma y is equals to 0 implies square root of modulus of x minus y is equals to 0. That implies square root is a 0 mean modulus of x minus y is equals to 0. Implies x minus y is equals to 0. Implies x is equals to y. So you can easily come in reverse order. You will get the d of x comma y is equals to 0. So what about the MS3? That is a symmetric property. The distance of x comma y is equals to square root of modulus of x minus y. That is equals to, what is this one? This is a square root of minus 1 times modulus y minus x. Just I took the minus 1 as a common. So I am using the property modulus of AB is equals to mod A times mod. So that's why this is modulus of y minus x, which is d of y comma x. So the third property, symmetric, is also satisfied, right? So then the triangular inequality. Let us take d of x comma y is equals to modulus of x minus y. Just I am adding z and subtracting z, that is x minus z plus z minus y. And we know that this value is by triangular inequality of the modulus, that is modulus of x minus z plus modulus of z minus y. Right? What happened for these terms? I am adding one more term, that is 2 times square root of mod x minus z times mod square root of mod z minus y. So this is a positive quantity. So this is again less than or equals to that value. So then this value is really what happened? This is a square root of mod x minus z plus mod z minus y square. This is a plus b whole square expansion, right? So what happened? This is, if I am taking square root on both sides, this one, and square it will be cancelled. Therefore, square root of mod x minus y is less than or equals to square root of mod x minus z plus square root of mod z minus y. So this implies d of x comma y is less than or equals to d of x comma z plus d of z comma y. So clearly triangular inequality is also satisfied, and hence here the R comma D, this D is a metric space. Okay? Right. Next one. Suppose I have a X is a metric space and I have a two matrix D1 and D2. There are two matrices. So you know that there are variety of metrics we can define on the non-empty set. So what is my question? So X comma D1 and X comma D2 is second problem in tutorial sheet. Two metric spaces. Right? What I am going to prove, remaining to prove, that D is a function from X cross X to R defined by D of X comma Y is equals to 2 times D1 of X comma Y plus 3 times D2 of X comma Y for all X comma Y belongs to capital X, the metric space. This is again another metric space on X. So as usual, you have to verify all four axioms, metric space axioms. So the first one, MS1, the D of X comma Y is greater than or equals to 0. It is true. Why? What is the D1 of X? D1 is a metric. D1 is a metric on X. That implies D1 satisfies all metric axiom MS1 to MS4. And similarly, D2 is a metric on X implies D2 satisfies all four axioms from MS1 to MS4. So in MS1, right, since D1 of X comma Y, D1 is a metric, so D1 of X comma Y is greater than or equals to 0, and D2 of X comma Y is always greater than or equals to 0 for all X comma Y belongs to capital X. So that implies 2 times D1 of X comma Y greater than or equals to 0 and 3 times D2 of X comma Y greater than or equals to 0 for all X comma Y belongs to capital X. So then their sum, that is 2D1 of X comma Y plus 3D2 of X comma Y, both are the sum is again also greater than or equals to 0 for all X comma Y belongs to X. So that implies D of X comma Y is greater than or equals to. So what about MS2? Same. We are using the metric axiom of D1 and D2. We are using in the D, right? So what is that one? In D of X comma Y is equals to 0 implies 2D1 of X comma Y plus 3D2 of X comma Y is equals to 0. This is a non-negative. This is a non-negative. Sum of the non-negatives are 0 mean the individual terms are also 0. So that is 3D2 of X comma Y is equals to 0 implies d1 of x comma y is equals to 0 and d2 of x comma y is equals to 0. Implies x is equals to y and here also x is equals to y. So totally that implies x is equals to y. So in the reverse you can use the same, right? And what about the uh, um, symmetric property M3 of yes MS3. So d of x comma y is equals to 2d1 of x comma y plus 3d2 of x comma. So d1 is a metric. I can write d1 of y comma x, and again d2 is a metric. I can write d2 of y comma x, because in when d2 is a metric, the second axiom obvious, right? Satisfied. So that is nothing but d of y comma x. So the last axiom, that is a triangular inequality. So we can simply verify based on the uh, d1 and d2 are both are metric spaces, right? So since d1 and d2 are metrics on x, so automatically it's satisfying d1 of x comma y is less than or equals to d1 of x comma z plus d1 of z comma y, and d2 of x comma y is less than or equals to d2 of x comma z plus d2 of z comma y, because d1 and d2 are metrics on x. Now we are going to prove our b is a d satisfies also triangular inequality. So what is that one? The d of x comma y is equals to 2d1 of x comma y plus 3d2 of x comma y. So that is equals to 2 times, that is less than or equals to 2 times. What is the d1 of x comma y? That is d of d1 of x comma z uh, uh, plus d1 of z comma y plus 3 times, and again d2 is a metric and satisfying the triangular inequality, that is d2 of x comma z plus d2 of z comma y. So I can separate, that is 2 times d1 of x comma z. Mm, uh, no need of this one. 2 d1 of x comma z plus 3 d2 of x comma z plus 2 d1 of z comma y, right? Um, plus 3 d2 of z comma y. So this is equals to d of x comma z plus d of z comma y. So totally the d of x comma y is less than or equals to d of x comma z plus d of z comma. So this satisfies all 4 metric axioms. So hence X comma D is a metric space, right? So that is. So next, the third problem. I think this one is explained in class, but however, I will explain. What is this set? So X is set of all 2 by 2 matrices, right? And mm, here, what is the matrices of the form? Suppose if I am taking set of all 2 by 2 matrices of the form 1, 2, 2x. This is the form, right? So that is simply set of all 1 to 2x such that x belongs to here, right? So, okay, let us take what is that one? Suppose a is equals to 1 to 2x, 2a, because a here a, and b is equals to 1 to 2b, and c is equals to 1 to 2c, right? Right, where a comma b comma c belongs to R, isn't it? So I am going to define metric, the define function d from x cross x to R by d of a comma b, that is a distance between these two metrics, is equals to modulus of determinant of a minus determinant of b. So what is the determinant of a? Determinant of a is uh, determinant of a is equals to simply a minus 2. Similarly, determinant of b is equals to b minus 2. Determinant of c is equals to c minus 2, like that, right? This is my function. What I am going to prove? To prove this, this d is a metric, and hence x comma d is a metric space. That is my target, right? So, as usual, what is our first axiom? Metric space axiom, non-negativity. So that is the distance between any two values should be a greater than or equals to 0, right? So now the MS1, that is a distance of a comma b, where A comma B are any uh, matrix in capital X in this form, right? So that is the modulus of determinant of A minus determinant of. So modulus value is always greater. Determinant of A is just a real number. This is one real number. This is another real number. So the difference of the real number is a real number. Modulus value is always non-negative. So that is greater than or equals to 0. So the first axiom is obvious. So what about the second one? So that is the axiom of coincidence, right? In axiom of coincidence, what we are going to take, let us say the distance of A comma B is equals to 0. What is that meaning? The modulus is modulus determinant of A minus determinant of B is equals to 0, right? So what is this meaning? Modulus value is 0 mean the inside value is equals to 0. That is the determinant of A minus determinant of B is equals to 0. That is determinant of A is equals to determinant of B. That implies A minus 4 is equals to A minus 2. A minus 2 or A minus 4? Sorry, this is A minus 4, right? B minus 4, C minus 4. So A minus 4 is equals to B minus 4. That implies A is equals to B. That implies matrix A is equals to matrix B. When A is equals to B, automatically that is matrix A is equals to matrix B, right? So you can also come in the same direction. We will get back the distance of A comma B is equals to 0. So what about the third property? That is the symmetric property, right? So in symmetric property, the distance of A comma B is equals to modulus of determinant of A minus determinant of. So in modulus, you can take a minus 1 of determinant of B minus determinant of A. So we know that the two product of modulus of two values is that is equals to modulus of minus 1 times modulus of determinant of B minus determinant of. So that is nothing but D of B comma. So in the same way, we can prove the triangular inequality. So what is the triangular inequality? MS form. So we will see the distance of A comma B is determinant of A minus determinant of, just as usual in the usual metric what we proved when it is a modulus, we need to add one value and subtracting another value. So that is modulus of determinant of A minus determinant of C plus determinant of C minus determinant of, again you apply the triangular inequality of the modulus, that is modulus of determinant of A minus determinant of C plus modulus of determinant of C minus determinant of. So this is nothing but P of A comma C plus T of C comma. So it is clearly that X is metric space, right? So now there is one interesting problem. What is that one? So we know that the C of 0 comma 1, that is the set of all continuous functions defined on closed interval 0 comma 1, right? So now there are two matrices. What is my matrix here? The distance d1 of f comma z is equals to integral 0 to 1 modulus of f of x minus g of x dx. And second one, d infinity of f comma g, that is a supremum of modulus of supremum of modulus of f of x minus g of x for all x belongs to 0 comma 1. So these are my two metrics on my space x is equals to c of 0 comma 1. That is the set of all continuous functions defined on the 0 comma 1. So what is my problem is here. So I have a two functions. Let f of x is equals to x and g of x is equals to x squared. So these are the polynomial, every polynomial is a continuous. So therefore, f comma z are the members of C of 0 comma 1. So no doubt. So my two functions are the continuous functions on closed interval 0 comma 1. So now what is my question here? I am going to determine the distance. So what is the distance between these two functions? These two functions under d1 and d infinity, right? So we will see what is the distance between d1 of f of x comma g of x, right? So now, so first you have to think about what is my x square. Which one is, I have x and x square. Which value is bigger one? Because all values are x belongs to 0 comma 1. So that's why x is always greater than or equals to x square, greater than or equals to. right? So in such a case, the x minus x square is always greater than or equals to 0, right? Okay, no problem. So now, what is my distance of f comma z? That is a d1 of x comma x square. That is integral 0 to 1 modulus of x minus x square dx, right? So x minus x square positive, I can remove that one. That is x minus x square dx. What is this value? That is integral x is x square by 2 and x square is x cube by 3 from the limits 0 to 1. So that is 1 by 2 minus 1 by 3 minus 0. That is 6 is LCM, 3 minus 2, that is 1 over 6. So the distance between the function x and x square is 1 over 6, right? Right. So the next one. The next one is the d infinity of f comma g. That is the d infinity of x comma x square. So let us say here, what is my function x minus x square? I call it h. H of x is equals to x minus x square. So x is continuous, x square is also continuous. The difference is also continuous. But what happened here? That h is a non-negative function. That is a greater than or equals to 0 for all x belongs to 0 comma 1. Right? Okay. So what is this one? This is nothing but the supremum of modulus of x minus x square, where x belongs to 0 comma 1. So that is nothing but the supremum of h of x, where x belongs to 0 comma, right? So what is the h? Since h of x is equals to x minus x square, which is a greater than 0, is continuous function on closed interval 0 comma 1, right? What is this 0 comma 1? Is a compact set. Once any continuous function defined on compact sets, that function attains maximum and minimum, right? So let us say maximum, right? So h of h attains maximum and minimum also. Okay, no problem, because here is a supremum. So we need to find the maximum value. So h attains maximum value where it attains the maximum. There are three possibilities. One is at endpoint x is equals to 0, or x is equals to 1, or critical point at critical point. This is our basic calculus course, right? Critical point, how do we get where h dash of x is equals to 0? So we know that simply maximum h dash of x is equals to 0 mean what is h dash? h of x is equals to x minus x squared, right? So h dash of x is equals to 0 mean 1 minus 2x is equals to 0. That implies x is equals to 1 by 2, right? So this is our maximum. Why? At x is equals to 0, h is equals to 0 and um, um, 1, it is a 0. So at x is equals to 1 by 2, we will get the maximum value, right? So h of 0 is equals to 0, h of 1 is equals to 0, and h of 1 by 2 is equals to how much that one? That is 1 by 2 minus 1 by 4, that is equals to 1 by 4. So your h as a maximum at x is equals to 1 by 2, that value is equals to 1 by 4. So this value is nothing but 1 by, right? Now, there is uh, one problem, the last one, in the examples of the metric space, right? So, what is here? So, let us take our metric space L infinity comma T infinity. So, L infinity is equals to our x. What is that x? L infinity is the set of all sequences, right? Set of all sequences. But what is not this is L infinity? That is set of all sequences, right? And what is the D infinity? We know that that is our supremum. That is D infinity of x comma y. So x is a sequence xn and y is a sequence that is a yn. So this is equals to D infinity of x comma y is the supremum of modulus of xn minus yn, where n belongs to set of all natural numbers. So we know that this is a metric space. Okay, that is a good, no problem. So now what is my question? So now what happened? I am taking a one subspace X is a subset of L infinity. What is this X? X is a consisting of all sequences Xn such that the terms of the sequence either 0, right? Such that terms of sequence either 1 or 0 or both. That is 1 and 0, right? So for example, I can take xn is equals to first term 0, 1, 1, 0, 0, 1, and so on. And yn is equals to this is my sequence x and this is my sequence yn is equals to, you can take 1, 0, 0, 0, 1. But whatever the sequences in the set X, all are either 1 or 0, right? So now What is that one? When it is a subset, so there is a metric. There is a metric. What is that metric? Induced, that is induced metric on X due to this D infinity. Right? Isn't it? So we need to find what I need. What is the induced metric on X? Right? So we will see. Right. So let us take two elements. That is, we know that d infinity of x comma y is equals to d of x comma y. What is the d here? What is the induced from this d infinity? That is we are going to identify, right? So we will see, let us take, let x is equals to xn, that is one sequence, and y is equals to yx, that is another sequence, that is members of x, right? So remember that all these sequences are either 0 or 1, right? Okay. So now the because this is x1, x2, x3, and so on. Here is y1, y2, y3, and so on. Isn't it? So I am going to calculate what is the distance modulus xn minus yn, right? So for each n belongs to natural numbers, I am going to calculate what is the modulus of xn minus yn. So this xn minus yn is equals to 0 when if the nth term of the sequence xn is equals to the nth term of the sequence in yn. Right? For example, here 1, 2, 3, fourth term, 1, 2, 3, fourth term, both are equal. Right? So that is 0. Suppose the next is 1, here is 1. 1 minus 1, 0. Right? So that is a 0. So 1, if xn is not equals to yn, because 1 minus 0 or 0 minus 1, you will get 1. So that nth term of the sequence in xn is not equals to nth term of the sequence yn in yn, right? So what we need to determine what metric d infinity of x comma y is equals to supremum of mod xn minus yn, right? Where n belongs to capital N, induces on x, right? So that is, here is xn minus yn is equals to 0 if xn is is equals to yn and yn is yn if xn is not equals to yn. What is the supremum? Right? So note that on x, we can have only either supremum of mod x minus xn minus yn, where n belongs to capital N, is equals to 0, or because here 0 or 1. Supremum of mod xn minus yn, where n belongs to capital N, is 1. Right? So, we know that if moreover, what we are going to determine, supremum of mod xn minus yn, where n belongs to capital N, is equals to 0 if and only mod xn minus yn is equals to 0 for all n. So that implies xn is equals to yn for all n. So that implies the sequence x is equals to y. And similarly, if the supremum of mod xn minus yn, where n belongs to capital N, is equals to 1, if and only if mod xn minus yn is equals to 1 for some n. So if and only if xn is not equals to yn for some n at least. So that implies our sequence x is not equals to y. So what is my induced metric? Therefore, induced metric D on x is defined by D of x comma y is equals to 0 when if x is equals to y, 1 if x is not equals to y. What is this metric? You know that metric. This is nothing but discrete metric. Right? This is a discrete metric. So what is that one? This is x is a subset of L infinity. Based on the entries of the subset x, that is that your D infinity metric induces a discrete metric. So this is my discrete metric which is obtained from D infinity by the nature of the set x, right? So that is the examples what we uploaded in the tutorial sheet, right? Okay. So now I need to stop here and then I will explain next open sets and closed sets.